simple harmonic motion of projection of the radius vector of rotating particle in V in each case, right? So we have these two diagrams, right? And this blue line, right? This blue line represents the initial condition. So the radius of the circle initial are indicated in the figures. Obtain the simple harmonic motion of projection of the radius vector of the rotating particle in each case, right? So B at t equal to 0. This is given. So initial condition is given, right? And we know that B at 0 is how much? What is B at 0?
I don't know.
So you see that P at 0 is this thing. So theta is, phi naught is how much? 45 degree, right? This is your P at t equal to 0. So your phase constant is this thing, right? Yeah, is it clear?
Yes, sir.
So if you look at this one, this diagram, right? Now they are saying that what would be. So now they are saying the projection of this P vector, right? So what would be that? So if you write, right, so project, let's say this OP, right, this OP, and let's say this angle is some angle, right? Let's say this angle is omega t, right? This OP has some angle omega t, right? And can you tell me what would be the projection of this thing on x-axis? What would be the projection? What would be the projection?
For 45 degree again?
No, so this OP, we want to calculate the projection of this OP, right? OP we want to calculate. So let's say you have a vector OP, right? This angle is some angle, right? And this is moving in this way. So this is omega t. So what would be this projection? Projection on this x-axis. What would be the projection? This is omega t. This would be OP cos omega, right? Right?
Yes, yes, sir.
Yeah. And whenever we are moving in this direction, so we take the angle be positive. So if we write, if we write this x vector, so this would be whatever the length of this OP is, right? The length of the OP is how much? Radius, yeah, what is the radius that we have? Depicts the radius of the circle, the period is A. So A is the radius that they have. Right? This would be A, and this is how much? So this would be omega. This would be cos and omega t plus 5. Right? This would be the projection. Is it clear? Because this is the initial condition, right? Phi naught, and this is the propagation of the wave that we have understood. A simple harmonic motion or periodic motion, right? And projection is cos theta, right? So this projection is cos theta. So this would be cos. And this is the velocity with which it is moving. And then initially it was here at phi naught. So it started from here and then it is rotating. So is it clear to you? Oh, so I guess Amna has also joined. Yes, Amna. So is it clear, everyone?
Yes, sir.
So A is here and omega. So you see that time period of this thing is 4 seconds, right? And what is the relation between time period and omega? What is the relation between T and omega? Time period is 2 pi by omega, right, guys?
Yes, sir.
So omega we can write as 2 pi by T. So if you write this thing in here, so this would be 2 pi T by T and plus this phi naught. Phi naught is how much? That is pi by. This would be how much? So if we represent this thing, so this would be A cos, and this T we know this is 4 seconds. This is 2 pi by 4 plus pi by 4. This would be how much? This is by 2, right? This would be simply how much? This would be A cos pi t by 2 plus pi by 2. So this would be the value, right? So this would be the projection of this vector. Is it clear, guys? Is it clear?
Yes, sir.
Okay, so what is the answer? So this is the answer. So 2 pi t by t plus pi by 2. So this 2 and 2 cancels and this would be value, right? So is this clear to all of you guys? Is this clear? Is this clear? Yes, is it clear, guys? This question.
Yes, sir.
Okay, so now you guys will tell me about because right. So now you guys will tell in the second question, right? In the second question, this is the. So you guys tell me that what is phi now? What is the phase constant? Initial condition. What is the angle that it is making at equal to 0? What is phi naught in the second figure? What is phi naught? This, in this case, the phi naught was 45 degrees, right? In this case, what is phi naught? Yeah, where is the blue line, guys? Where is the blue line? Line is the initial condition. Pt equal to 0. This is the blue line. So, what is the initial phase constant? What is the angle, guys? With the horizontal, what is the angle? Is it clear now?
Yes, sir.
What is phi naught? It's phi naught, pi by 2, right? And now, if you look at, so now this is traveling in this direction, the opposite direction. It is not traveling this way. So then this x would be how much? That would be A and cos of and pi by 2, right? And this would be minus omega. Is it clear? Because generally we write it as A cos omega t plus phi. When the movement is in this direction, right, anti-clockwise. But when they are moving clockwise, then we have to take this as minus. This is what we have, right? This is dependent function. So this is the thing. And now we know that cos 90 minus theta is what? Sine theta, right? And t value is 30 seconds. So omega t is 30 seconds. So omega would be how much? That would be pi. 5t, which is 30. So if you write this value, so x would be how much? That would be a sine and 2 pi by this 30 seconds into t. So this would be how much? So this would be pi by 50. So a sine pi t by 50. This is the second. This one for the second. Is it clear, guys? If it is clear, then quickly note it down. Quickly note it down, guys. And if you have any question, please let me. Okay. Is it clear, guys? And please note it down and tell me whenever you guys have noted. So this is for the first diagram, and this is for the second diagram. This is very important. If you guys have any difficulty in understanding, please tell me. Because we know that what is the periodic motion, right? Or the SHM. So we know that SHM is simply a cos omega t plus phi naught or sine omega t plus phi. We are taking the projection on the x-axis. So this would be cos omega t plus phi. And then we have to figure out phi naught, and then we have to figure out this time period. So omega is related to time period. We put these values, and then we get the answers. So these are the two important things. Whenever you guys have noted it down, and if you have any questions, still done, guys.
Yes, sir.
Bhavna, what about you? Noted.
Yes, sir.
Okay, so now, yeah, then this is now let us do a very important question. And you guys please revise this chapter. Right? Okay, and did you guys make this diagram? Did you guys make this diagram? So whenever you guys get time, please make this diagram. Okay, so in the last class, we understood about this simple pendulum motion, right? And yeah, I stopped at this point, right? I left at this point. What was the last part that I left at this point, right? So I left at this point, so then we can also calculate the time period, right? And we already know that what is the time period of oscillation, right? If we calculate the time period of this thing, okay, what is the why? So what is the simple harmonic motion that we got? We got this relation. This is minus m l by I, right? And this is how much? This is theta. So if we remember, right? If we remember, what was uh, what was the time period of oscillation? This was 2 pi, right? Root m by k. This was the time period of oscillation, right? And if we compare this thing, so what is this thing? This is omega square, right? Omega square is mgl by I, right? And we know that how this omega square and k is related, right? So we know that k is m omega square, right? So if we put this value in here, right? So k is m into omega square. So if we put this value in here, so this would be 2 pi and m, and this is m omega square. So what is value? This is m. Omega square is m g l by I. So this part will cancel. And we know that this for this mass, right? For this mass, this thread is of negligible mass. So if we calculate the inertia of this mass, so that would be simply the product of this mass into this length square. So I would be simply, I is how much as we know, I is simply m and l square, right? And do you guys remember what is the time period of simple pendulum from the dimensional analysis? What was the time period of simple pendulum that you got? You guys remember that? This you have done in also in the school experiment, in practical part. What was the time period of oscillation of simple pendulum? Yes, guys. From dimensional analysis, what is the time period that you get? Okay, so let me solve this thing and then you guys will tell. So then the time period that we will get would be I is ml square and this is mgl. So m and m cancel, l and l cancel, and we get
So I don't know about with dimensional analysis, but normally it's 2 pi root of LG, I think.
l by g, right?
L by G, yes.
Yeah, so this is what we are getting, right? This is what we are getting from this simple harmonic. So yeah, you guys please note down this part that what would be the time period of right. So this is without using the dimensional analysis. You guys please note down this part. And then we'll do one question which is important and then we'll start the next chapter. Next chapter is waves, right? And when that chapter would be over, so then it will take only a few classes to complete this. Quickly, you guys quickly note it down, and if you guys have any question, then please tell me, right? Because remember, what was the acceleration, right? Acceleration is minus omega square theta. This is the angular acceleration that we have compared. So if we compare this, then omega square will be this. And from omega square, we calculate k, and then we put it in here, and then we calculate the time. So, yeah, quickly note it down, guys, and then one. Yeah, whenever you guys have noted it down, then just have to compare with the linear acceleration. So in the linear acceleration case, we got this. Okay, whenever you guys have noted it down, do that. Yes, noted, guys. Done.
Yes, sir.
Yes. What about you, Amna? Noted? Yes, Amna, noted.
Yes, sir.
Okay, so now let us do a final question. This is very important. And yeah, so let's say that if you guys remember the mechanical properties of the fluids, right? So let's say that we immerse, right, some cylindrical object in this. So you guys already know that, let's say this is pressure 1, this would be pressure 2, right? And the difference between these two pressure would be how much? So what would be this P1? That would be equal to how much? P2 plus rho GH. This was P1 minus P2. Difference in pressure was how much? Rho GH. Right. So this is the pressure that we feel at certain depth. And this pressure is in upward motion. So due to this pressure change, we get a buoyancy force, right? The upward force that we get. So the FP that is acting on this thing, that equals to how much? So let's say this is equal to VGH, right? Or this is equal to V. This is V. This V rho and G. This rho is the density of the liquid. Whenever whenever you immerse some object in liquid, so it feels an upward force. That force is called the buoyancy force, right? Do you guys remember that part? Do you guys remember this thing? So this comes from
Yes.
the yeah, this comes from the Archimedes principle also, right? This comes from the Archimedes principle. So now we have a question, right? We have a question which says that we have a liquid of density. So we have a liquid of density, let's say rho, and you are immersing a cork, right? So we have this glass bottle, and on top of this glass bottle, we have this cork. So if you immerse this cork, right, in this, and this is cylindrical shape, right? So this is a cylindrical shape cork, and let's say if you immerse it in x distance, right? In x distance, you have immersed it. So then you have to calculate that. Then you have to show that this cork will move up and down, right? So this cork will show simple harmonic motion, right? So this is the equation, and you guys can find this question in NCRT part, and this is the last question of right. So this is a cylindrical piece of cork of density of base area A and height h floats in a liquid of density rho r. So the density of liquid is rho r, and the cork is depressed slightly and then released. Show that the cork oscillates up. Okay, so what is the density of? So rho is the density of the cork, right? Show that the cork oscillates up and down and simple harmonically with a period this, right? So ignore damping due to viscosity of the liquid. So viscosity we have to, yeah, we don't consider the viscosity. So then we have to calculate what would be the time period of that oscillation. So we have this liquid, right? We have this liquid, and you guys have seen that if you put some cork and you press it, so it will come out, right? So then we have to show that cork will show a simple harmonic motion. That is the thing that we have to show. Is it clear? And remember, we are not completely immersing this cork. So this is immersed in this x distance, right? This is the thing that we have to find out, and we have to find out the time, right? So first thing that we have to prove that force would be how much? Force should be how much, guys? What should be the force? This is showing simple harmonic motion. So what should be the force, guys? This should be directly proportional to minus x.
Yes, sir.
So this we have to show first. So let us solve this question here. We have this cork, right? And what is providing the restoring of force, right? So if we are pressing this cork in x distance, right? So if we are pressing this cork in x distance, so the force which is pulling it upward, which is providing a restoring force, so that would be the buoyancy, right? That would be the buoyancy force, right, guys? Why this is not right, guys?
Yes, sir.
So the force restoring is F buoyancy. Right, and this F buoyancy, we know that is how much? So that would be minus of F buoyancy is how much? This would be minus F buoyancy. So this would be how much? That would be V, and rho of liquid, right? And they are saying that rho of liquid is rho R, right? And then G. So this is the value that they are saying, right? And we know that volume is how much? What would be the volume which is immersed in this liquid? So that would be area into height x, and this is rho r, and then this is g. So this is how much? This is minus a rho r g and x. So f is this a is constant, this rho r is constant, g is constant. So f is proportional to what? Minus x. So this will show what? SHM. Is it clear?
Yes, sir.
Right, and volume, yeah. So volume, we have to know that volume is how much? Volume immersed would be this base area into this height. So this height is x. So volume is area into height. Right, and this height is the height that you have immersed. So this would be now we know that what would be this? So f is minus x, right? Now if we put the value of f, so f we know that this is ma. MA is minus A rho R G and X, right? So this would be how much? This A would be minus A rho R G X, and this would be M. And we also know that what would be the mass of this? What would be the mass of this cord? Mass is how much? Density is how much? Density is how much?
Mass by volume.
Mass by volume, right? So then we can calculate mass, which is V, and we know that volume of this cord, volume of this cork is how much? That is area A, and this height of the cork. So this is AH. So if we put this value in here, what we will get? We will get minus A rho R G divided by A rho H. And this is X. So this A and this A will cancel. So A is how much? A is minus rho R G by rho H and X. So what is the general solution? General solution is minus omega square X. Right, guys? Right?
Yes, sir. Yes, sir.
So then we can calculate omega square as rho R G by rho H. So omega is root of rho R G by rho H. So we have got omega, then we can calculate time period, which is 2 pi by omega. This would be 2 pi, and this we have to take the reciprocal. So this would be rho H by rho RG. So this would be the time period of oscillation of that quark. So that quark will will show a simple harmonic motion, and yeah, it will come out of the liquid and then go into the liquid. So it will be like that, right? So is this thing clear? Is it clear, guys?
Yes, sir.
This is question number. This is yeah. So 2 pi rho h by rho r. So they have written rho I. This is rho r, right? So 13.1 question. And this one is important question. That's why I discussed this. This is question 13.1. Please note it down, guys. And if you have any doubt, please note it down. Yeah, whenever you guys want me to slow down, that. This restoring force is actually provided by this F buoyancy, right? This minus is coming due to this X, which is in the opposite direction, right? That is why this minus is coming. So we should not write it in here. We should write this minus in here. This minus is coming due to this because we are pressing this thing downwards, but the force is upwards. So that is why this minus is coming, right? This F buoyancy is upwards, which is providing the restoring force, right? So this is equal what the direction that the displacement is moving. So displacement is happening in downward direction. That is why this minus is here, right? Okay, whenever you guys want me to scroll down, please select it. Yeah, whenever you guys want me to scroll down, please select it.
Done, sir.
Okay, then yeah, whenever you guys have wanted it down. Yes, noted everyone.
Yes, sir.
Good. Okay, so now let us start. So this chapter is over and we have done some questions as well, right? So now let us start the next chapter, which is, and the first thing that will be the understanding, right? So velocity of wave and particle, right? Okay, so the first thing that comes into our mind, right? So let's say uh, that would be a different, right? So let's say if I'm speaking in a room, right, and the person which is in front of me, so how is the person is able to hear me, right? How can the other person is able to hear me? Something is taking my voice sound wave to the other person, right? So that is how he is able to understand or he is able to hear, right? So those my energy of sound wave and that is reaching to the other person. So the means to transport my sound to the other person, that means is called the wave, right? So it is the means transfer the energy from one person to another person, right? So it is a means to transfer the energy. That is all the wave is about. Right. Let us understand that more clearly. Okay, so what is a wave? Right. So it is uh, or is a means to transfer the energy. Right. And how do we transfer the energy? So what kind of transfer will takes place? So let's say that if we are transferring the electrical energy, right? So then if we are transferring transfer of electromagnetic energy, that would be called electromagnetic. And the example that I gave, right? The example that I gave, so transfer of sound energy. So that would be called sound, right? So wave is what? It is a mean transfer the energy, right? So how the energy propagates from one person to other person, that is called the wave, right? And then how this wave motion takes place, right? So how this wave motion takes place. So there are two parts of wave motion. This is very important. There are two parts of wave motion. One is that particle in the medium is oscillating, and then the wave is moving periodically. Then actual wave is moving periodically. So how to understand this thing? Let us take the example of sound. Right. So let's say we have this loudspeaker. Right. We have this loudspeaker. So we have this loudspeaker and sound waves are coming out of it. Right. And then we have this person. So it says here. Right. So sound wave is so sound is generating from here. Sound is generating from here. Sound energy. And then this sound is reaching to this person. So between these loudspeaker. So this is the loudspeaker, and then we have this receiver, right? Receiver. So in this case, this receiver is ear, right? And then between these loudspeaker and this ear, there is this these particles, right? So what is happening to these particles whenever this sound wave originates? So this oscillate these particles, right? These oscillate these particles. So these particles move periodically, right? They move periodically. So this move in this way. So this move in this way, and this move in this way. So they move periodically and then simultaneously they generate a wave. So this is how the sound wave from, right? So two things are happening in wave motion. One is that this is moving, this is showing oscillatory motion. So these particles are showing oscillatory motion. And due to the oscillation of these particles, this wave is carried out and then it is reaching. So that is how we are able to hear this loudspeaker voice in this right. So these are the two basic part of wave motion, and we have to be very careful with that. So one is that wave is moving periodically, and particle in the medium is oscillating. So this is how the wave propagates, right? Then how many kinds of wave that we have? So kinds of wave that we have. So types of wave. So there are mainly three types of wave. One is the electromagnetic wave. And the other one is this mechanical wave. And then the other one is this matter wave. Right? So electromagnetic waves, the important point of this electromagnetic wave is that they don't require material medium propagate. Right? So this is the electromagnetic waves. And then we have this mechanical waves, right? For example, the example of mechanical waves, so they require. And what is the example of electromagnetic waves? So we have light, right? So light doesn't require any medium to propagate. So light is the one of the example of electromagnetic. And then what are the mechanical waves? So they require material medium propagate. Right, and the example are what? So example are sound waves, and then we have seismic waves, and then we have water waves. So all these are examples of mechanical, right? And then this matter wave, so this is generated due to this de Broglie hypothesis, right? So these are shown by electron and protons, right? So waves are generated by these electrons, movement of those electrons. So this part you guys will study in the 10th, the 12th standard, and this part you guys will also study in the 12th standard. So we will study about those waves which require material medium to propagate. So we'll study about this mechanism, right? So this part we'll study in this class. Okay, so we know that the mechanical waves require material medium to propagate, right? So we will have two things. One would be the particle motion, oscillatory motion, and then would be the wave which is moving periodically, right? Okay, so now we have talked about the kinds of wave. Now there is this, so what kind of wave motion that we have, right? So kinds of wave motion, right? So let's say that you guys have, guys must have seen this Yes, can you guys hear me? Hello, am I audible, guys?
Yes, sir.
Yeah, so kinds of wave motion that we have. So one is transverse wave, and the other one is the longitude, right? So what you do is that let's say you guys have seen these gym videos. So let's say you have this rope, right? You have this rope. This rope is there, right? This rope is there, and then this person, you guys have seen that this person moves this rope in this way, right? So this part is fixed, but this rope is moving like this, right? Did you guys yeah, have seen these kind of videos? So those athletes, what do they do? So they fix the other end of the rope, right? And then from this part, they provide some initial force, right? So they move it like this, right? So the particle of, so this is the initial position of the particle of these ropes, right? So this is the initial position. But if these ropes are moved like this, so particle is moving in this, right? The particle, so these are the particles, and this is the particle, right? So this is how the particles are, right? Let me make this diagram in this way, right? So draw it from this. So we have this is the transverse, right? So what we are doing, we have this, right? We have this fixed thing, and we have this rope, and we have fixed this end of the rope, right? And these are the particles of, and then we are moving this rope from here. So we are Yeah, my diagram is pretty bad. So this is the diagram. And this rope is moving like this. So this is the movement of the rope, right? So we can say that the particles are moving in y direction, right? And this wave is traveling in this direction. So the propagation is along this direction, right? But the particle are moving in y direction. So the movement of the direction of the particle is y, and propagation of the wave is in x direction, right? So what is the angle between the propagation and the movement of particles? What is the angle? What is the angle between the movement of the particles and the propagation? What is the angle? Oh, both of you guys got this. Yes, yeah, Amna, can you hear me? I guess Rishta got disconnected. Yeah, so did you guys, yeah, so did you understand this part? So we are moving the rope in this way, but the propagation of wave is moving in this way, right? So this is how the particles are moving. This is how the particles are moving, and this is how the the wave of the rope is, right? So the propagation is taking place in this direction, in X direction, but the particles, right? So these particles are moving in Y direction. So whenever these kind of waves are generated, so these are moving in, this is called crest, and this is called trough, right? So whenever in these kind of wave propagation, the direction of propagation is perpendicular to uh, the displacement of the particle, right? And the waves move in crest and trough, right? So they move in crest and trough, right? So this is how whenever these kind of propagation are there, so these are called a transfer, right? And then the second one is called, so the example of this transverse wave is what? So example is this example is your light waves, right? And then you have these water waves. So these are the example of transverse wave, and then you have this longitudinal wave. So in longitudinal waves, what happens? So let's say you have this spring, right? You have this spring. You have this spring, right? And what you do is that you compress this spring. So you'll get two kinds of situation. So one would be that your spring is this way, and then you will see the spring is this way. So one part would be compressed, and the other part would be relaxed, or right. So whenever the waves moves in this way, so one part is compressed, right? And then the other part is relaxed. So this is called compression, and this is called rarefaction, right? And the movement of the particle is in this way. So movement is also the movement of particle is in this way, and the propagation is also in this way. So this is the movement of particle, and propagation of wave is also in the same direction. So whenever these kind of waves are there, these are called longitudinal waves. So in this kind of motion, the wave or the propagation of wave is in the same direction as the particle displacement, right? And these kind of waves travel in longitudinal or travel in compression and rarefaction, right? So this is the example of the longitudinal wave is what? So example of longitudinal wave is sound. So sound waves travel in compression and rarefaction, right? And the water waves or the light waves, they move in Christ and trough. So whenever the propagation of wave is perpendicular to the direction of the particle motion. So particle motion is moving in this way, propagation is happening in this way. So this kind of motion is transfer wave, and whenever these are traveling in, so the direction of propagation and the movement of or the movement of the particle, they are in the same direction. So this is called longitude. So these are the two kinds of wave motion, right? You guys please note down from here, and then we'll talk about the velocity of wave and particles. Please note it down. And whenever you want me to scroll it down, please tell me. Let me zoom out this thing. Right? Yeah, and whenever you guys want me to scroll down, please click. Yeah, whenever you guys want me to scroll down, please tell.
So can you scroll down?
Yeah, whenever you guys have take it down.
So can you scroll down until the start of transverse wave?
Start of class. Yeah, whenever you guys have noted it down, please.
So can you scroll down?
Yeah, so this is here relaxed, and then again we will have
So what's the second last sentence? Compression and
rare fraction. Rare fraction. This is rare fraction. Then this part is compression, and this part is rare fraction. This is how the longitudinal wave travels, right?
done, sir.
Then, okay, so how do we write or how do we represent the traveling wave, right? So the representation of traveling wave. And this is the displacement of the particle that we're talking. So displacement of this particle y. What is this y? So y is represented as a and sine and kx minus omega t plus 5, right? Or if so, this is written right. Or if we write it like this a and sine a sine omega t minus kx plus 5, right? So these two represents the propagation in positive x direction, right? And if I write the displacement of the particle as this a and sine kx plus omega t plus phi naught, or if I write so a sine omega t plus kx, or I write minus omega t or minus x, right? So if I write it like this, then these two are showing that this is propagation in negative x direction. These two things we have to be very careful of, right? So, and let's say if they write a wave like this, a and sine kz minus omega t plus phi. So, in which direction the wave is propagating? Can you guys tell me? What is the direction of wave propagation?
Negative. I mean left side.
This is kz minus omega t. So, this would be in z direction, positive z direction, right?
Yes.
Yeah, so whatever is in there, and if it is in alternate in negative sign, so this would be the direction. Yeah, so just remember this. So what are so let us take we are propagating in x direction. The wave is propagating in x direction. So let us take the displacement in this form. Right. Y is a sine and kx minus omega t plus phi. So then what are the things that we have? So A is the amplitude or maximum y distance, right? Amplitude of oscillation, right? And then this K is angular wave number. This angular wave number K is related with this lambda, right? So this K is 2 pi lambda, where lambda is the wavelength of propagation, or the wavelength of the. So lambda is the wavelength. And then we have this omega. So omega is angular frequency, and this is related with the time period, right? So this is related with the time period, and this is time period of the wave, and this omega is related as 2 pi by t. This is how this angular frequency is related. And then lastly, we have this phase constant. This is the phase constant. Right, we'll talk about these things in the next class. Yeah, in the next class, we'll talk about all these things. You guys, please note down these parts. Right. And yeah, in the next class, we'll do some question about this. Please note it down. Yeah, whenever you guys have noted this part, right? Yes, whenever you guys have noted it down, please.
Done, sir.
Done. Okay, so what about you, Amna? Noted.